The 11-dimensional unveiling superposition as a systemic illusion of incomplete perception. The perplexing phenomenon of quantum superposition, wherein a particle seemingly exists in multiple states or locations simultaneously, until the act of measurement forces it to adopt a definite reality, has long stood as a bastion against our classical intuitions. This inherent probabilistic nature of the quantum realm has fueled countless interpretations and challenged the very foundations of our understanding of objective existence. However, the 11-dimensional model, with its expansive framework encompassing a hierarchy of interconnected dimensions, offers a compelling alternative perspective. That superposition is not an intrinsic, paradoxical feature of reality itself, but rather an emergent illusion, a consequence of our limited, lower-dimensional perception of particles existing within a far more intricate and deterministic multidimensional landscape. By mapping a particle's fundamental properties onto the 11 dimensions, we can begin to unravel the complexities of superposition, revealing it as a natural outcome of the particle's dynamic interactions and our incomplete access to its full, higher dimensional state. At the heart of this re-evaluation lies the understanding that a quantum particle is not an isolated entity confined to our familiar 3 spatial dimensions and linear time. Instead, it is an integral component of a larger, interconnected system, its behavior intrinsically linked to the multidimensional fabric of reality described by the 11-dimensional model. This framework posits that a particle's properties, from its intrinsic spin to its apparent positional variance, are not static, inherent qualities confined to a single point in spacetime, but rather dynamic manifestations of its movement, orientation, and interactions across these 11 interconnected dimensions. Let us begin by considering the particle's spatial existence within the first 3 dimensions. While we perceive a particle as being located at a specific point in space at any given measurement, the probabilistic nature of its positional variance, as described by the wave function, suggests a fuzziness, a lack of definite location until observed. Within the 11-dimensional model, this apparent positional uncertainty could be a direct consequence of the particle's inherent participation in larger systems, as governed by the higher dimensions. Even a seemingly isolated particle is invariably interacting with at least the observer or the measuring apparatus, a 2-body system whose dynamics are influenced by the 6th and 7th dimensions of orbital motion and its modulations. Furthermore, the particle exists within a broader environment, a 3-body system at the very least, subject to the influences described by the 8th and 9th dimensions. These multi-body interactions, even at the quantum level, introduce inherent variances in the particle's trajectory and its probability distribution in space, potentially giving rise to the illusion of positional superposition when our measurements capture only a limited snapshot of this dynamic, system-dependent behavior. The 4th dimension, intricately linked to rotation and the fundamental passage of time, introduces another layer of complexity. For a quantum particle, spin is a primary characteristic within this dimension, manifesting as the binary polarity of up or down along a measurement axis. This initial spin state, defining the particle's fundamental rotational orientation in the 4th dimension, also lays the groundwork for the 5th dimension, embodying the particle's inherent polarity. We have previously explored the analogy of the Djani-Bekov effect, a macroscopic phenomenon where a rotating object with asymmetric inertia exhibits sudden flips in its rotational polarity. At the quantum level, analogous, albeit far more rapid, oscillations or sampling of a particle's polarity within the 5th dimension, occurring on timescales far beyond our macroscopic resolution, could manifest as the time-averaged probabilistic outcomes we interpret as spin superposition. The particle is not truly in both spin-up and spin-down simultaneously, but rather its fundamental polarity is rapidly evolving, and the limitations of our measurement tools prevent us from resolving this underlying deterministic fluctuation. Furthermore, the higher dimensions, particularly the 6th and 7th dimensions governing 2 body systems, and the 8th and 9th dimensions governing 3 body systems, introduce the crucial aspect of interaction. A quantum particle is never truly isolated. It exists within a network of relationships, even if that network includes just the observer or the measuring apparatus. These interactions, occurring within the multidimensional space of the 11-dimensional model, inevitably influence the particle's spatial and polar properties. The positional variance we observe as superposition could be a direct consequence of the particle's dynamic participation in these larger systems, its movement and probabilistic distribution in space being a reflection of its interconnectedness within the higher dimensional web. The observer, far from being a passive bystander, becomes an integral part of the system through the 2-body interaction described by the 6th and 7th dimensions, influencing the particle's manifestation in our observed reality. Finally, the 10th and 11th dimensions, representing the cosmic context of expansion and contraction, provide the ultimate backdrop for the particle's existence. The subtle influences of these all-encompassing dimensions could further modulate the particle's intrinsic properties and its interactions within smaller systems, contributing to the overall observed quantum behavior. The interconnectedness of the 11th dimension, potentially allowing for non-local influences and instantaneous information exchange, might play a crucial role in the seemingly correlated behavior of entangled particles. Their superposed states resolve into definite outcomes in a linked fashion that defies classical explanations. Therefore, within the expansive framework of the 11-dimensional model, superposition emerges not as an inherent paradoxical feature of individual particles, but rather as a systemic illusion. It's a consequence of our limited lower-dimensional perspective on particles existing within a far more intricate and deterministic multidimensional landscape of dynamic polarities and interconnected interactions. If we could fully account for a particle's state across all 11 dimensions and its complex choreography within this higher dimensional space, the probabilistic veil of superposition might very well dissolve, revealing a deeper, deterministic reality that underlies the quantum enigma. Thank you for watching. If you enjoyed the content, please like, subscribe, and share.